All right, so we're going to begin. Last lesson we met a geometric sequence. And what was the important feature of a geometric sequence? The important feature, of course, make sure you're listening now. The important feature of a geometric sequence, of course, was that the ratio between consecutive terms remains constant. So the other way we would write that is the ratio is always equal to Tn divided by Tn minus 1. Or you could have Tn plus 1 divided by Tn. The ratio between consecutive terms is constant. That is the definition of a sequence that is geometric. We knew that already. Today, we are going to look at a geometric series. You will remember from our work on arithmetic series and sequences that the difference between a sequence and a series is that in a series, we add the terms together. The sequence is just the list of terms in order. A series is adding the terms. So you can say what is the geometric series, or you can say what is the sum of the first n terms in a sequence. And that's effectively asking the same thing. So what we want to look at is there a nice way of finding the value of a geometric series? A plus AR plus AR squared plus AR cubed, all the way through to the nth term, which of course is AR to the n minus 1. And we're going to call that, just as we did for an arithmetic series, capital S for the sum or series, and n, Sn, the sum of the terms in that sequence becomes the series. I'm going to write it over on the left because that's where we usually like to write those things, is when we write the subject. And obviously, we can do this just by adding up terms. Is everyone happy that we might be able to do that? If I make up a little example now of a geometric sequence and I ask you to find the sum of the first 5 terms, I reckon you're all going to be able to do it. So we've got a sequence here. Find the sum of the first 5 terms for the sequence above. And I don't think any of you are having trouble with this, are you? And we can write that as 7 3/4, but we don't really like mixed numbers, so we're going to write it as 31/4. But either of those would be fine. I'd be happy. You'd be happy with that question in an exam. That's nice giveaway marks, isn't it? If I said, find the sum of the first 73 terms in that series, or in the sequence, who's going to be as excited about finding out that sum? It is less appealing to go through and continue doing that and adding all those little tiny fractions together. It's not going to be any fun. So we want to find another way of doing that. Quite clearly, there's a rule for it. I wouldn't be talking to you about this, and you can see up there what the rule is, but we're going to derive the rule from our general sequence, because that's going to be more important for us to be able to derive this rule. So I'm going to, if it lets me snip that, there we go. So here we have the sum of the first n terms, and we are going to derive the rule for finding that sum in a nice, easy, and convenient manner. Now, apparently, Ms. Kinnear reminded me that last time I tried to do the sum of an arithmetic series with you, I lost you all along the way. So I'm going to try not to get too excited and go too quickly, and we're going to go through this together. You'll see it's actually quite nice. There's something a little bit tempting about this series I've got up the top there, and that is, if I could, there's a common factor in there, isn't there? Can everyone see a common factor in the list of terms there? Yeah, of course you can. There's an A, and almost every term's got an R in it. Only the first term is really missing. So that there's going to be a little bit of factorising involved. And we're going to show you a neat little trick for the way to prove this sum. What I'm going to do is I'm going to create a series that is almost the same as that one. What I'm going to do is I'm going to take that series and I'm going to multiply everything by the common ratio. I'm going to multiply everything by the common ratio. Now, if I do that to the left-hand side, I have to do that to the right-hand side. So my first term, A, when I multiply it by R, is going to be A times R. My second term is going to be AR squared. My third term, AR cubed. My fourth term, AR to the 4, etc. Up to that very last term, where I'm going to have AR to the power of N. Now, I'm actually going to include the second last term just because it's going to make some things a little bit more clear for you. But you can see the terms which match up there when they get multiplied by R. They're producing the term underneath. Are we all happy that that line, the second line there, is the top line multiplied by R? I've shown an extra term in there, but we're all happy with that. Now what we're going to do is we've got two equations. We're going to do some simultaneous equations because we've done this before. I'm going to take this second expression and I'm going to subtract the first expression. I'm going to go, what do I get? Equation 2 and I subtract equation 1. The left-hand side, I'm going to have R multiplied by my series minus the series. Are we all happy that if I take the R times S of n minus Sn, it just looks like that? Yeah. When I do the other subtraction, I'm going to have a look carefully at what's going on. This AR term corresponds to the second term in the sequence above, doesn't it? When I'm doing subtraction, what's going to happen with those two terms? I'm going to have AR from the bottom term minus AR from the top term. That's going to go to 0, isn't it? If I have AR squared and I subtract AR squared, that's going to go to 0. AR cubed minus AR cubed, that's going to go to 0. This AR to the power of 4, the next term up the top would have been AR to the power of 4. That's going to end up being 0. This second last term in my bottom sequence, A times R to the power of n minus 1, when I subtract A times R to the power of n minus 1 from the top expression, that's going to cancel as well. What am I left with? I am left with AR to the power of n minus, I've just got that little first term that I didn't deal with. Are we happy enough? We can see that so many of the terms are the same. They're all cancelling out. All I'm really left with is the last term from the second expression minus the very first term from the top expression. Now, factorising looks like it might be useful. I have to insert more space. So on this left-hand side, you can definitely see Sn as a common factor. The remaining factor is R. Don't forget that there's a 1 here, isn't there? There's one Sn in the right-hand term, so it's R minus 1. On the right-hand side of my equation, the common factor is A. The remaining factors are R to the n minus 1. We can now find an expression for Sn. Sn is going to be A R to the n minus 1 divided by R take 1. Now, remembering that often we use A for the first term, but what's the other thing they use in your formula booklet for the first term? T1. I could just as easily write that as the first term, the ratio to the power of n minus 1 divided by R take 1. And that's my expression for the sum of the first n terms of a geometric series or a geometric sequence. There's an alternate way of writing it, and I'm going to mention it because it can make our life easier in some instances. If I just multiplied the top and bottom of each of that right-hand fraction by -1, I would get that expression. A times 1 minus r to the power of n divided by 1 minus r. And again, if we use our T1 notation from the QCAA course, 1 minus r to the power of n divided by 1 minus r. We've got the same expression. Why do you think it might be useful to sometimes use the top expression and sometimes use the bottom expression? That was a great answer. I'm going to say it louder for everyone. To avoid negatives, particularly in our denominator, right? We don't like having negatives in our denominator. Great answer. So I'm going to use this top expression when my ratio, the absolute value, so it's positive or negative, I can still have a negative ratio. We looked at that the other day. When that is greater than 1. So when the magnitude, the absolute value of my ratio is greater than 1. I'm going to use the bottom expression when the magnitude of my ratio is less than 1. That way, I'm keeping the denominator positive. It's not that you'll get the right or wrong answer using either one. They both yield the correct answer. But our working is easier and we'll make fewer mistakes if we choose to have it the right way around when we do it. What you don't want to do is mix the top line from one of those rules with the bottom line of the other. That would make you cry. And your maths teachers. Yeah, and it's in your formula sheet.
So if you make that mistake, you're an idiot.
There you go.
Let's not fluff this.
So you've got at the bottom there an example 18. I want you to have a go now. Find the sum of the first 12 terms of that series, that geometric series. I'm going to pause. You're going to have a crack at it right now. All right. So coming back together, let's make sure we've been able to do what we need to do for this question. We need to identify my first term, which is 2. You can see I didn't erase the previous working there. The ratio, if I do the second term divided by the first, or the third term divided by the second, the ratio is always 3. I'm interested in 12 terms. That's telling me n equals 12. So if I substitute those into the equation, did we indeed get 531,440? Maybe? I can hear a lot of chat, but no one telling me whether they got that number or not. We did. Thank you. Doing much better than those boys in the middle table. All right. Another one for you to have a go at, please. Example 19 there. Have a go at that one now. All right, so coming back together, let's make sure that we're all in agreement here. Rather than just writing -3 up here, I think it's probably important that you communicate this a little bit in an exam situation. So it'd be nice if you wrote the ratio was Tn plus 1 divided by Tn. You could have written T2 divided by T1. I'd have been happy with that. And then you can go ahead and come up with your ratio being -1/3. I just think it's a little bit safer. Then we're going to substitute into our formula. It's a little bit small there. Let's just make it a little bit larger. My first term was 9. My ratio is -1/3. As Ms. Kinnear was reminding you, it's very important you have that -1/3 in brackets so you don't do an incorrect calculation. Once you've done that, which rule did we find it easy to use? 1 minus r hopefully. You could do it with the other one. They still work. But 1 minus r makes your life a little bit easier. And we go ahead and look, it wasn't even finished. Well, that's the sum of the first n terms, which is all they asked us to do. Then if they wanted the first 10 terms, you just replace n with 10. If they wanted the first 5 terms, you replace n with 5, and so on. That's all there is to it. It's not an overly complicated rule. We know where it came from. It's also on our formula sheet, so that's useful. We're good there. There's one more rule we need to learn for geometric series. And this is one of the most enjoyable rules to think about because it doesn't make a lot of sense until we see a proof for it. So,
All right, guys, this is going to be important. It's going to be tied into probably CU questions, all right? Always gets tied in there. Kind of thing that you just need to be listening, understanding. We will do it again, but be really on board with this one because this, I can guarantee, will appear as a CFCU question in context of something. It really lends itself well to it.
So we're going to find the sum of an infinite geometric sequence. So a sequence that does not end. So we're always going to be adding something onto this sequence because the sum of the terms in a sequence, sum means to add. And we're going to, the claim is we can find the sum of an infinite sequence, which might be a little bit confusing at first. So I'm going to need a volunteer. Who's going to volunteer for us? Grabsky, good man. Well, I saw you twitch. Okay, you need to stand up for us. This is an active job. Okay, I want you to where can we? You're going to walk towards Miss Kinnear. So I want you to get like in a straight line. Start over near Oscar there. Now your job is to halve the distance between yourself and Miss Kinnear as best you can. Let's assume do you reckon you did pretty well there? I reckon you did pretty well. All right. I think that was pretty good. Could you do that again, please? Okay. Now, for the remainder of the lesson, we will stay here, and it's probably a little bit awkward because I'm getting to walk towards you. Maybe just walk towards her desk and Miss Kinnear take a step backwards. But halve the distance between yourself and the desk again. And could you do that again, please? And could you continue to do that until you are actually touching the desk without ever actually doing more than half of your distance between you and the desk, please? In theory, could you do it?
Yeah.
Yeah, we could continue halving that space, however small the space is. You could halve it and get closer and closer to the desk. Eventually, we're not going to be able to tell the difference between whether you're touching the desk and not touching the desk, are we? But we do know how far you will have traveled, and that would be the total distance from where you started to that desk. So we can find the sum of an infinite series by measuring the value of what value he's getting closer and closer to until he's so close we can't tell whether you're there or not. And that's effectively what we're going to do with this. You were a great help. Thank you very much. It's a pity that the YouTube didn't pick that up as well. That would have been exciting footage for everyone, especially once I realized that I really needed to change the object. So how does this work? Let's say the first step there, I'm going to estimate this. The first step was 3 meters. The second step, the first step, half of the total distance was 3 meters. The second step, he was halving his distance each time, 3/2 meters. The next step, dividing by 2 would be 3/4 meters, 3/4 of a meter, wouldn't it? Half of 3/4 of a meter, 3/8, 3/16, and so on. Are we all happy that that was the sum of the distances, assuming his first step was the first distance he traveled was 3 meters, and we're halving it each time? Are we all happy that that's the sequence we're finding, the sum of all those terms? So let's use our sum of the first n terms. I'll use the T1 version of the formula because I want to try and encourage you to use the formula you're going to be given in the exam. What information did we have here? We know that T1 is equal to 3, and my ratio, I obtained that by doing the second term divided by the first term. And because I actually explicitly spelt it out that I wanted him to halve his distance, we already know that's a half, don't we? Now, how many terms did I say I wanted you to find the sum of? All right, well, infinity is not a number, but it's a concept. Let's just use the idea of infinity as saying I'm going to let that number be as large as possible. Are we all happy with that? Make the substitutions into that equation, and let's have a look at what we get. So, S, instead of n, I'm going to write infinity, the infinite sum, the sum of the infinite series, is going to equal my first term there, 3. 1 minus, my ratio is 1/2. What am I going to do when I substitute that ratio in? I'm going to put it in brackets, good people. Are we happy that that's the expression we have? I'm pretty happy with that. Let's see what happens when I simplify that a little bit. I want to talk a little bit about 1/2 to the power of infinity, if you like. What happens if I consider that expression 1/2 to the power of infinity? I'm sure you're all happy using our index laws, but I could consider it as 1 to the power of infinity divided by 2 to the power of infinity. Is that reasonable? I think that's reasonable. Well, what's 1 to the power of anything? It's still going to be 1 on the top, isn't it? What's happening to my denominator? It's getting bigger extremely quickly, isn't it? We know our powers of 2 climb very quickly, and we're taking an infinite number of those. So basically, if I'm taking 1 unit, let's say 1 piece of paper, and I've got to share a birthday. I was going to take 1 student and pull them apart, but I thought that was a bit too mean. Oh, no. It's too messy for the nice new classroom. So a birthday cake, but we had to share it with everyone. Between 2 people, I could just cut it in half. Then I take those halves and cut them into half. And I take those quarters, cut them into half. They're now 8ths. Cut them into half again, 16ths. I could continue cutting each of those pieces indefinitely, couldn't I? Eventually, how much of that birthday cake are we going to receive? If we take like our little Coles mud cake, because I'm pretty tired, so it's got the $4. Or maybe I'm even lashing out. We'll go the Cheesecake Factory cheesecake, because I like that one. If I split that up with, say, everyone in this class, you'd still get a little bit of a taste, wouldn't you? Wouldn't be heap. It'd be small. There's nearly 60 of us in the room, but it'd be okay. If I split one little cheesecake between, say, all of year 11, is it almost worth turning up to get your little share of that cheesecake? Maybe, but that's only what, 300 of you.
Only because you're
300. That's only just a little bit more than 2 to the power of 8. If I start splitting that one little cheesecake up with everyone in Brisbane, are we getting much of a feed? Not really, are we? And then if I continue thinking about how much you're going to get if we use it, split it up between everyone in Australia, or everyone in the world, or every person and animal in the, and that's even very small compared to infinity. How much are you effectively getting? Nothing. A fraction, a number between 0 and 1, or between even -1 and 1, if you want to think about the absolute value of a fraction, as that fraction is raised to the power of infinity, that number is approaching 0. We've actually seen that before when we've considered our hyperbolic functions, haven't we? And we're approaching 0 as our asymptotes. So,
I've just got a quick question though to ask you. Let's say it wasn't the number 1 on top. Would that affect it? So let's say instead of it being the number 1, it was the number 3. If you did 3 over 2 to the power of infinity, so you got 3, or something like not 3 over 2, let's
You
say,
mean-
what would happen if it was 3 over 2? It would get bigger. Okay, what happens if I had 3/5? Okay, what happens if I had 10/3 to the power of infinity? Bigger. Okay, so what do we notice is key? What is the relationship that's key here? So if I had 2/3, 2 to the power of infinity, 3 to the power of infinity, which number is bigger, the top or the bottom? You have 2/3, 2 to the power of infinity, 3 to the power of infinity. So is that number going to get bigger or smaller? Smaller. So what's the relationship you've got to be thinking about? There we go.
yeah, so summarising what Miss Kinnear was saying there, in general, the infinite sum of a geometric sequence will just be my first term divided by 1 minus r, because that r to the power of n term that we have in the original formula is going to approach 0, but only when the absolute value of our ratio is less than 1. When I'm multiplying by a positive or negative fraction between -1 and 1. That's when it will have an infinite sum that I can calculate. If my ratio was 0, I can also calculate it because we know, after the first term, every term's 0. So that's the trivial case we don't really need to consider. But that is going to be important. You can find the sum of an infinite geometric sequence, the sum of the terms in infinite geometric sequence, provided that the ratio of terms in that sequence is less than 1. Does anyone have a handball in their pocket, boys? Yeah, who's got one? Oh, someone does, surely. Is this not the handball crew? Jürgen, you didn't bring a handball? Mahir? Oh, well, you miss out on listening to the sound of a geometric sequence. You've all dropped the ball before, right? No, never. You've heard one drop when you were playing with, I don't know, Potsy. Oh, harsh, but fair. If you drop a ball and let it bounce, what happens to the bounces? It gets smaller. Did you realize that they were in geometric sequence? Now you do. Because the ball, the coefficient of restitution, how far it's going to bounce up, is always a fraction of the original height from which it's dropped. So when you hear that noise of a ball bouncing, like being dropped, and then just continuing to bounce, you know how it gets really close together until you can't tell when it's bouncing and when it's not, because it just sounds like, and then eventually it stops, as far as we can see. That's the distance the ball travels we can find using an infinite geometric sequence. It's pretty cool.
So, Mr. James, I gave you a good CFCU question there. Hope you all absorb that.
It will definitely appear. That's the favorite application question.
I've seen one where Ant walks around and continues to walk in a circle.
Yeah, it's like spiraling down a funnel or something. Yeah, same sort of thing. That's where I'm going to leave it today. That was exercise 14B and 14C. There you go. That's exciting.
We'll go through it.
So you guys have now an opportunity to just try a couple of questions or ask us any questions, and then make sure we're all set for next time.